Hey everybody, welcome to my third video on set theory. Today I'm going to be introducing topics that are typically covered before the topics that I covered in the last video, but I just wanted to show you guys a little bit about infinite sets and cardinality and stuff like that you can do with sets. So now let's go a little bit back to more of the basics. I'm going to teach you how to write sets algebraically, because in the first video we talked about how to draw a set and how to show it. But now we're going to talk about really how to write sets. So sets are pretty easy to write. Let's say we have a set, A. This can be a set of things, we have little a1, little a2, little a3, and maybe little a4. Okay, so let me talk a little bit about convention. So capital A is a set. We typically denote sets with capital numbers, or capital letters. And then lowercase letters are typically elements of that set. And a lot of the time, we're going to choose letters that are basically the lowercase versions of the same letter that denotes our set. Now, it doesn't have to be that way, but it often is. So that's why I have A1, A2, A3, and A4. With, of course, the subscripts meaning they're different elements. So this is the first, the second, the third, and the fourth. Now, there doesn't have to be an order on the sets. You can have ordered sets, but that's a whole different thing. So this is the same as if we did, A3, A1, A4, A2. Something like this. It's the same set, okay? It doesn't matter what order everything's in. So this is a really good way to write sets, and it makes a lot of sense. What if we had, though, even numbers, a set of even numbers? So I can call that set E. So the set of even numbers, we can write it as something like, let's say positive even numbers, just to make it easier. So we have 2, we have 4, we have 6, we have 8, 10, and we can keep going, right? Obviously we can't put every single positive even number, but we can kind of just keep going. So we can kind of write it kind of like that. But this isn't really that good, because sometimes, we typically want to try to avoid having ellipses, I think that's what they're called. We want to try to avoid those. Not always, but just sometimes it's better to write it in a more concrete way. So how would we do that? Well, there's another notation called set builder notation. What that does is it allows us to write a set in such a way where we have a sort of condition. So here I can say, okay, well, the set of even numbers, let me write that brace a little better. We can write that as 2k, where k is an integer. And this is actually so I'm going to say k is a natural number, just so we can restrict it. And natural numbers not including 0 in this case. So what I have here, so first off, I want you to understand that any even number can be written in the form 2 times k, where k is an integer, or in this case a natural number, because 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, and so on and so forth, right? So any number basically is divisible by 2, so we can write it this way. And so notice how I have this colon. Sometimes people write it like that, like a bar in the middle. I like to put it like this sometimes, but it just depends. And so we have basically this is the set of all these things with this condition, okay? And so that's how we write in set builder notation. I don't think it's too difficult to understand. We can just basically write it like this. If we want to say the set of all things that are one less than a power of 2, so we can denote a set. Let me call it R. I don't know why, just R. So this can be the set of things that are 2n minus 1, where n is an integer. Okay? So anything that's 2 to the n minus 1, anything in that form where n is an integer. So 2 to the first minus 1, 2 to 2 squared minus 1, 2 cubed minus 1, 2 to the fourth minus 1, 2 to the 1642 minus 1, and just anything like that. Or even 2 to the negative 5 minus 1. Just anything like that, I can represent it like that. And this is a lot easier than representing it by writing things down, because sometimes the pattern really isn't obvious. In this case, the pattern is super obvious, but in this case it might not be. So it's really good to try to use something better than just ... you know? So yeah, that's why set builder notation exists. And again, I can write this as a vertical bar. It's up to you. I try to make the vertical bar a little big so it's not doesn't look like a 1 or an absolute value thing. But you typically don't want it going past the height of the curly brace, so something like that. Okay, so that's power. That's set builder notation. Let's move on to power sets now. So what is a power set? So let me write that down. So actually, this is set builder. Set builder. Sorry for the sloppy handwriting. So that's set builder notation. And now we're going to move on to power sets. So power sets are typically, if we have a set X, so if we have a set capital X, then the power set is denoted with like a curly P. I tend to write it as something like that. So P of X, where X is a set. This is the set, actually I'll just write it, is the So P of X is a set of all subsets of X. So what that means is basically if we have X equal to, I don't know, 1, 3, 4, and 2 or something like that, yeah. Then basically, actually let me limit it to three elements for now. So then P of X is, we would say it's every single subset. So the first is, I would say, obviously 1. 1 is a subset, and we have to include these curly braces because each of these things are sets, okay? So, well, subsets, and we put curly braces around subsets. So we have the set containing just 1, the set containing just, actually I don't have 2 there, I meant 3. And then the set containing just 4. And then we also have the set containing, we have the set containing 1 and 3. This is another set. We have the set containing 1 and 4. And I can keep going. We have the set containing 3 and 4. We have the set containing all of them, so that's 1, 3, and 4. So that's the entire set. And yes, the entire set, it is a subset of itself, right? We're not talking about proper subsets, we're just talking about every single subset. So 1, 3, and 4, that is a subset of itself. And here's one that's often forgotten. It is the empty set, the set containing nothing. That is a permutation of our subsets of X. So it's 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so, and so we have to have that last curly brace, so these two. And so yeah, so there are 8 total elements, so we can say that the size of the power set of X is equal to 8. And in general, it is, so we have the power set of X. Actually, I'll say the power set of some other set. I'll say B, any set B, or actually I'll use S to denote a set. The power set of S is 2 to the n, where n is just the number of elements of S. So in other words, we can write this as 2 to the size of S. Just like that. So this is, and another way to denote the power set is just 2 to the S. You can write it that way. But yeah, so that's about power sets. You basically any permutation of them. What's interesting is that we can have power sets of n, the set of natural numbers. So this is an infinite set, right? So you'll have stuff like all the singletons, which are just the sets containing one element. So we have 1, 2, and so on. And then we have stuff like 1 and 2, and so on. And I'm writing super sloppy here, but whatever. And so yeah, just basically anything like that, you can represent. You can basically take the power set of any set, because that's actually an axiom of set theory. It's like built into set theory. If you're following Zermelo-Fraenkel, the set theory axioms from them. But yeah, so this is power sets, and yeah, so that's pretty much all I want to say about power sets. I think you get the idea of set builder notation as well as power sets. So let's move on to some examples of some really important sets. So the first example I want to talk about is one that I've already discussed. We have n, the set of natural numbers. So it definitely has 1, 2, 3, and so on. And again, I can kind of write this in set builder notation. Okay, and sometimes it has 0 depending on the context. And this is hard to write in set builder notation without being circular, because you can say, oh, you know, it's every number in the natural numbers. It's pretty circular, but we'll just go from there. You can talk about exactly what this is using the Peano axioms. So I can write that down. You can look at the Wikipedia article on that. And then Z, the set of integers, is pretty much the set. I mean, it's just, you have 0, 1, -1, 2, -2, and so on, right? So pretty much the same thing, just kind of definitely with 0 as well as all the negative numbers. And then you have Q, the set of rational numbers. So this is very easy to write in set builder notation. It's every number written a over b, such that a is an integer and b is an integer. So if you have this, it's every single a over b where a is an integer and b is an integer. So that entire set forms the rational numbers. And then you have R, the set of real numbers. So I don't really have to talk about that much. That's pretty much any number you've dealt with. And then you also have complex numbers, which is C. And then you have stuff like R, you have R squared. Oops, you have R squared, which is just equal to R times R, which I haven't discussed, but really that just means the two-dimensional real numbers. And then you have Rn, which is just R times times R times R. So just n times, basically. That's a really lopsided one here. So n times. So basically it's n-dimensional real numbers. And same thing you can do with these or any other set. You can take capital N squared. That's just the two-dimensional integer real numbers. And then, yeah, there are a bunch of other sets. There are the quaternions, which is, I think, typically denoted H. If you don't know what they are, then don't worry about it. And yeah, you can have any sets. You can have, let's see. I don't know what other interesting sets I should talk about, but let me talk about this a little bit. So this is what's known, this multiplication here, this is what's known as the Cartesian product. I forgot for a second. Yeah, this is the, so I'll just say Cartesian product. And it comes from Descartes. And what it is if you have A times B, this is basically every single thing that's A multiplied by B, every element of these where, and I can write it like this, where A is in A and B is in the set B. So you can kind of see the advantage of having these letters be the same, just this is capitalized, because you can really easily tell which comes from which set. So anything that's a times b, normal multiplication here, where a comes from a and b comes from b. So any basically like that forms the Cartesian product. And that's what this is, just two-dimensional real numbers where you have a coordinate pair. Here it's n-dimensional real numbers where you have n tuples of things. And then you can have like complex numbers like that and all that sort of stuff. But yeah, so that's pretty much, I think, everything I want to talk about with the examples here. You can think about any other sets that you want. You don't have to have sets of numbers, you can have sets of things. Let's say we denote a set, I don't know, T. This is a set of, I don't know, you can have like letters E and Q and television and stuff like that, whatever you want. You can draw a picture, just like whatever you want. It doesn't matter what you have. It's just a set will contain anything. It's just typically in math, it's numbers or variables or any other thing that might be useful. So yeah, that's pretty much all I wanted to do today. Thank you guys so much for watching, and I'll see you in the next video. Bye guys!